Today I'm going to go through your Unit 9, which is all about series, your test review. So first up we have sigma notation, and expanding sigma notation and then eventually finding a sum. So in sigma notation we always start by plugging in the value that's on the bottom. So this one's starting with a -2. And then add that to the next term, which is going to be the next number higher. So we'll have a -1 in that spot, we'll have a 0, and our last one is going to be a 1 because that is our ending value. So this would be expanded. You could also write it as -4 plus -3 plus -2 plus -1, and if you add all these together you get -10. Here our starting value is 1, so we're going to end up with 3 to the 0 over 2 plus 3 to the first over 2 plus 3 squared over 2. We'll keep going until 3 to the 4th over 2, which is 20. Forget about that one. So the last number we plugged in was a 4, so we get that 3. But we still get a sum of 20. All right, our next one, our function is just 2. So we're going to plug in 2, we'll get 2. If I plug in 3, we get 2. If you plug in 4, 5, 6, 7, and 8. So there's 1, 2 for each of the numbers between 2 and 8. For a total of 14. The next questions we're going the other direction. Okay, we're going to write this in sigma notation, and a useful tool is our nth term formulas for arithmetic and geometric. So this one is arithmetic, so the nth term formula, okay, is that. So I can plug in the particulars here. So that'll be 52 plus n minus 1 times our common difference. What we're adding here is going to be 4. Okay, if I distribute that, we'll have 4n minus 4. So we end up with 4n plus 48. Okay, so in my sigma notation, that's my general term. We are starting at 1, and then the last thing we need to do is figure out our ending value, what value I'd need to plug in to get that 84. So we'll just set 84 equal to 4n plus 48, subtract 48 and divide by 4, gives us 9. Okay, the next one over here is geometric. Okay, so that general formula is a1r to the n minus 1. This is going to be 1. My common ratio is 1/3. So we'll start at 1. My general term, we don't necessarily need to write that 1 anymore. So this will be 1/3 to the n minus 1. Then we want to figure out what we need to raise really 3 by to get 729. When you do that, you'll end up with n equals 7. So 3 to the 6th is 729, so my n will be 7. And you have a calculator to do this with. Okay, next up we have infinite limits. So there's kind of two camps. There's the rational functions, which is a polynomial over a polynomial, and then ones where the base is an exponent. So for these ones, we're looking for the degree. Here the degree is bigger on the bottom than the top, so this is going to go to 0. Here the degrees are the same, so the ratio of the leading coefficients is what I'm going to look at. And then this last one, the degree is bigger on the top, so it's just going to grow faster and faster, so it's either infinity or does not exist. This limit does not exist because it's not going to a specific value. For these ones, if our value is between -1 and 1, like this one, it's going to go to 0. If it's bigger than 1 or less than -1, it's going to grow faster on the top than the bottom. So this is going to be non-existent. Okay, and -1 to the end, that's just going to bounce between 1 and, or -1, 1, -1, 1, -1, 1. So since it's not approaching 1 value, we say that that limit does not exist. Okay, now we're going to find the sum of the series. So first what we want to do, when it's written in sigma notation, it's nice to write out a couple of terms. So if I plug in a 0, this will be 1, so this is just going to be 2. If I plug in a 1, we're going to have 4/7. If I plug in a 2, one with 8/49. Okay, so our common ratio here is 2/7. That's what we're multiplying across the top and the bottom to get these terms. That's good news, because that is between -1 and 1, which means we can find the sum using our sum formula, which is always a1 over 1 minus r. So my a1 is 2 over 1 minus r, 2/7. So this will be 2 over 7/7 minus 2/7 will be 5/7. So this will be 14/5. Okay, this next one, if I expand it, we'll have a 3, 9 over 2, 27 over 4, and so on. This one's common ratio is 3 over 2, which is not less than 1. So this one has no sum. Okay, if that common ratio is not between -1 and 1, we're done. Here, we'll have 2 over 25 if I start at 1, then we'll plug in 2. We'll plug in 3. Okay, so our common ratio is 2/5, which is between -1 and 1. So my sum will be 2/25 over 1 minus 2/5. So this will be 3/5. So we'll have 2 over 25 times 5 over 3. We can reduce those 5s, and we end up with 2 over 15. Okay, this one, if I write it out, we'll have 3, e over 1 is just e, plus 3e squared plus 3e cubed. E is not a variable, e is a number. E is approximately 2.718. Well, my common ratio here is e, which is greater than 1, so again, there is no sum. Okay, this next one, sine of 5 pi over 3 is just on our unit circle. So if I go to the y value at 5 pi over 3, that's going to be a -√3 over 2. So this series, if I plug in 0, is going to be 1, then we'll have a -√3 over 2, plus a 3 over 4, and so on. So my common ratio is -√3 over 2, which is between -1 and 1. My a1 is 1 over 1 minus a -3 over 2. And you could simplify this down further, but we're just going to leave it like that. Okay, this one, if I were to plug in, we get 3 minus 2 is 1. If we plug in 2, we'll get 4. Plug in 3, we'll get 7. Okay, so the terms are getting bigger and bigger. And in fact, this is arithmetic, so we cannot find an infinite sum of an arithmetic series. All right, next up, we have a power series. This power series has a common ratio of 2/3 x. So for the interval of convergence, that ratio needs to be between -1 and 1. Then we want to solve this for x, so I'll just multiply by 3 halves. So -3 halves is less than x is less than 3 halves. The function represented by this series, this is really just asking for the sum. We'll write it in function notation, so that's going to be a1 over 1 minus r, which is still 2/3 x. Okay, and again, you could simplify it, but I'm going to leave it just like that. These next two, we're going to use this equation to evaluate if we can, meaning we can only plug in values between -3/2, -3 halves and +3 halves. So is -1 in there? Yep, so we're good. So we're going to have 1 over 1 minus 2/3. -1. So this will be 1 plus 2/3, which will be 5/3. So if we're reciprocal, will be 3/5. 7 halves is not between -3 halves and 3 halves. So we cannot evaluate the function. Okay, so the next question, suppose you were given the following information. What could you determine about the divergence of the series? And explain in your own words why this is true. Well, if I do this one, if I look at the limit as n goes to infinity of Sn, okay, if I look at this limit, as we go to infinity, it has the same degree, so it's going to be 5/4. So this one converges, because if the sums have a limit, then the series converges. These are the partial sums. So this is saying we're adding a lot and lots of terms, but the sum just stops at 5/4. In fact, the sum is 5/4. But on the test, you need to do this in your own words. Okay, this next one, if I do the limit as n goes to infinity of an, the equation is the same thing. The limit value is going to be the same thing, but what we are taking the limit of is very, very different. So we're still going to get 5/4, but this is the individual terms. If I'm keeping adding terms and they're approaching 5/4, that means I'm adding an infinite number of 5/4. So this would diverge. Okay, and again, you would explain this in your own words, why it would diverge. Okay, next we have a variety of different series here, and it may be helpful to write out some of the terms, but we're trying to determine if the series converges or diverges and why. Okay, this first one is going to be arithmetic. Which means it will be divergent. The terms are going to keep going either up or down, but they're never going to approach 0, which is necessary for the series to converge. This one and this one, these are both infinite geometric series. Okay, the common ratio can be found here in the parentheses. So the common ratio here is 6/5, which is bigger than 1. So this one is divergent. This one's also infinite geometric, with a common ratio of -5/6, which is between -1 and 1. So this one will converge. This last one, anything over n, is considered a harmonic series. And harmonic series always diverge. Okay, now we're going to make a table of ordered pairs for the partial sums. Okay, we're doing the sums, not just the individual terms. So if I add the first one term, which is 2, we'll have 2. If I add 2 and this will be 2, we're going to get 4. And past this, we can just use the calculator to help us. So you'll add the first 3 terms, which is going to be 5.33. Next term would be 16 over 4 factorial, which is going to be 6. And then you just keep adding them on. So again, use your calculator. We get 6.27, 6.36. So they started increasing, but they're kind of leveling off here. And if you need to do more terms to figure out that pattern, you can. Okay, so that's 7. So we're going to graph these, 1, 2, 3, 4, 5, 6, which will emphasize the fact that this is going to level off. So 1 is at 2, 2 is at 4, 5.33, 6, 6.27, 6.36. Okay, if we continue, it's going to go to about 6.4. So the next part of this question says, does the sequence appear to have a limit? And we're going to say yes. Okay, about 6.4. Okay, what, if anything, can you say about the convergence? Well, if it's approaching a value, then the series converges. Okay, finally, we have some tests for convergence, and this is how it's going to look on your test. Is you're going to be told which to use. You just need to know how to use it and then what conclusion you can make. So the divergence test, or the nth term test, you are looking at the limit of the nth term, or in this case the kth term. So I want to write that down. So we're going to have 3k squared over, if I FOIL out that denominator, we're going to have 5k squared minus 4k minus 1. That limit is 3/5. Okay, divergence test says if it does not equal 0, then the series is divergent. Here, if I do the limit as k goes to infinity of ak, that's going to be the limit as k goes to infinity of 1 over 3 to the k. That denominator is going to grow way faster, so it's going to go to 0, which means it could converge, but we don't have enough information. So it is inconclusive if we get 0. Okay, for the ratio test, we're still using limits. Okay, we're going to have the limit as k goes to infinity of the kth plus 1 term over the kth term. Okay, so we're going to have 2 to the k plus 2 over k plus 1 factorial over 2 to the k plus 1 over k factorial. Okay, so we're going to do a couple things in this next step. Okay, I'm going to rewrite this as 2 to the k times 2 to the 2 over k plus 1 factorial is k plus 1 times k factorial, and then we'll multiply by the reciprocal, which will be k factorial over 2 to the k times 2 to the 1. So the k factorials cancel, the 2 to the k's cancel, and I've got 4 over 2, so I'll just say that's just going to be 2. So this is now the limit. As k goes to infinity, we're left with 2 over k plus 1. Okay, now I've got something that we can deal with here. So this limit is 0. For the ratio test, we're comparing to 1. That is less than 1, so this one is convergent. If it's bigger than 1, then it is divergent. This next one I don't have a formula, but I can see I've got 1, 2, 3, 4 on the bottom. So let's say n on the bottom, and then above that is going to be n plus 1. Okay, so we've got the limit as n goes to infinity of the nth plus 1 term over the n. So if this is our nth term, my next term would be n plus 2 over n plus 1 over n plus 1 over n. So we're going to have n plus 2 over n plus 1, and then multiply by the reciprocal here, n over n plus 1. We'll have n squared plus 2n over n squared plus 2n plus 1. Okay, that limit is 1. And unfortunately, that means we don't know. Okay, it's going to be inconclusive. The last test that we have is the comparison test. So we're going to take this, and I'm going to compare this to 1 over 2 to the k. Okay, I'm choosing this because this one is an infinite geometric series with a common ratio of 1/2, so it's going to converge. But I'll deal with that later. I'm going to build the comparison. So 2 to the k plus 1 will be bigger than 2 to the k. So if I take the reciprocal, that will be less. So this series is less than this series. Okay, this one is an infinite geometric series with a common ratio of 1/2. And if you need to write out some terms to see that, do so. That means this one converges. And if the bigger one converges, that means the smaller one has to converge as well. Okay, so those are the steps I'm looking for. I'm looking for build a comparison, make your conclusion based on your new series, and then what implication that makes. Okay, so we've got one more of these. So we've got 5 over 3, 5 over 4, 5 over 5. So this would be 5 over n plus 2. So I'm going to compare this to 5 over n, because that's harmonic. Okay, n plus 2 is greater than n. So 1 over n plus 2 is less than 1 over n, which means 5 over n plus 2 is less than 5 over n. So this series is less than this series. Okay, and this one is harmonic, therefore divergent. Okay, however, if the big series diverges, it's not super helpful, because if the big one diverges, that doesn't tell me anything about the smaller series. So again, this is an inconclusive test. Okay, so those are the things that you need to be able to do to be successful on your Unit 9 pre-calculus exam.